Okay, welcome back. Today we're going to finish up linear momentum. Where we left off last was with propellers. We're going to start today with wind turbines, which is basically a propeller acting in reverse. And then we'll look at accelerating control volumes. And then we will take a break and we'll move on to conservation of energy. So just to recap, we applied Reynolds transport theorem and the continuity equation to a moving control volume. And one of the applications of a moving control volume are propellers and wind turbines. So they both work on the same principle. There is a stream of fluid and a rotational prop is increasing the linear momentum of that fluid by increasing its velocity. And the reaction of that is a force that acts on the propeller, and that what we call our dynamic force. And we can also call this thrust. So for a propeller, when we apply our equations, we end up with these two equations where we have our force, which is the thrust on the fluid, is equal to rho times pi times the radius swept by the propeller squared divided by 2, which is just rho times the area of the propeller divided by 2, times the difference of the velocities squared, where v1 is the velocity entering our control volume, and v2 is the velocity exiting our control volume. And we also derived Froude's theorem, which says that the velocity right at that prop, so velocity at point 3 and point 4, so right here and right here, just in front and just behind the prop, that velocity is more or less constant, and it's equal to the average of the velocities entering the control volume and exiting the control volume. So for a moving control volume, if this is a propeller, it's attached to a boat, the velocity entering would be equal to the velocity of that boat because it would be moving through water that would be stationary, and relative to the control volume, the water would be moving into the control volume at the rate that the boat is moving forward. And that is the concept that we use to derive our equations for efficiency. So the power output would be the thrust of the propeller times the velocity that the boat is moving, which is equal to that V1 entering the control volume. So our output power, W0 dot, is F times V1. And the power input is the rate of work needed to maintain that increase in velocity from V1 to V2. And if it requires the fluid to have a velocity V through the propeller, then the input power is the force, or the thrust, times the velocity, which we can calculate from Froude's theorem as the average of V1 and V2. So if we substitute these in together, we get these two equations for for the ideal efficiency of a prop is either is defined as the work output divided by the work input, which is equal to 2 times the velocity 1 divided by velocity 1 plus velocity 2. So if we were to look at this equation and see, how do we increase the efficiency? We can increase the efficiency by getting useful work without changing the velocity stream as much. So if we imagine, maybe scroll back up here, if we had a control volume and our velocity input was equal to our velocity output, and we were able to harness some sort of thrust out of that, that would mean we were able to get some kind of thrust without actually changing the momentum of the fluid. We would have a 100% efficient motor or propeller. Since that's impossible, the efficiency of the propeller will always be less than 100%. And the greater the difference between the input velocity and the exhaust or the ejected velocity V2, the lower our efficiency. Talked about a few notes on propellers and their efficiency. We did an example. So let's now start with wind turbines. So wind turbines and windmills, they do the opposite of a propeller. They extract the kinetic energy from the wind or from the fluid. So the flow pattern for these devices is just the exact opposite of a propeller. So now we have our input velocity V1 is entering a narrow stream tube, and then it passes through our wind turbine blades or our turbine blades, and then the profile exiting our control volume is V2, and that has a reduced velocity. And if we apply the same equations as before, we can also use Froude's theorem. So Froude's theorem, just to write again, is that the velocity at the blade is equal to the average of the input or the inlet and exit velocities. And if we apply this, then we get the same equation as before, except you'll notice now that the V1 and the V2 are just flipped. So instead of having a V2 squared minus V1 squared, we have V1 squared minus V2 squared. And this is the force acting on that fluid. So here we have a parcel of air passing through the blades. We define the area swept by the blades as pi r squared. R is the radius of those blades. Let me draw that on here. Call this R. And has a velocity v. So the power output is F times V. So before, when we had a prop, F times V was our power input. Now that's our output power. And if we substitute this back into the equation above, and we get our output power is equal to 1/2 rho VA times V1 squared minus V2 squared. So this result, if we could think of it as representing the rate of loss of kinetic energy of the wind. So if we are harnessing the kinetic energy of the wind, the rate that we are harnessing that energy, the rate that the kinetic energy is being lost by the wind as it passes through the blades, will be the rate of the work output from the system. So to calculate efficiency, we need to find the work input. So the rate of work input, or the power input, is the time rate of change of the kinetic energy of the wind passing through the area swept by the blades. So if our mass flow rate m dot is equal to the density of the fluid times the area times V1, that is entering our control volume, then our work input is equal to 1/2 m dot V1 squared. And if we just make our substitution for m dot above, we have this equation for our work input. So work input is equal to 1/2 times the mass flow rate times the velocity entering squared. So essentially the kinetic energy, or the rate of kinetic energy. So the ideal efficiency is again calculated the same way. We have our rate of work output divided by our rate of work input. So we take our two expressions and we simplify, and we can get this equation over here, which is in terms of our input and our output velocities, as well as the velocity v, which is at the blade. And if we substitute in Froude's theorem for the velocity of the blade as v1 plus v2 over 2, for the average, we can get our final equation down here. This big mouthful, 1/2 of the product of 1 minus v2 over v1 all squared times 1 plus the ratio v2 over v1. So that gives us the efficiency of our turbine. So the efficiency of turbine, if we plot that as a function of the ratio of v2 over v1, we'd see that the curve passes through some maximum point. And this point happens to be when the efficiency of the turbine is 0.593. And this happens when the exit velocity divided by the entrance velocity is 3. So there is a maximum efficiency of a turbine. And in other words, the maximum amount of energy that a wind turbine can extract is 59.3% of the total power of the wind. And this is actually known as Betz law, named after the German physicist who derived it many, many years ago. So we can classify wind turbines by their rated power and also by wind speed. And those currently used in industry, they rate them based on something called a capacity factor. And the capacity factor is a ratio comparing the actual power output for a year of operation to its related continuous power output for the year. So the actual power output for a year divided by if it was running continuously for a year. And the actual is just because there is variation in wind through time. It's not always the same amount of windiness throughout the entire year. So modern wind turbines have capacity factors, and they're usually between 0.3 and 0.4. So the actual power you can extract from running it continuously is only about 30 or 40%. So for efficient operation, wind interference between neighboring turbines also has to be maintained. So if you put the wind turbines too close, the interference is going to deter or take away from their efficiency, their capacity to generate energy. So we have to make sure that they stay at least about 10 blade lengths apart. So when we look at wind power, we usually have to conduct a feasibility analysis of the wind power. So the feasibility of harnessing wind power at any location depends on the average annual wind speed at that location and the wind power density. The wind power density is defined as the annual power available per square meter of swept area by a wind turbine. And we can tabulate this for different heights above ground. And there's actually charts. I think the next slide shows a chart provided by various organizations that actually map out average winds at different elevations from the ground. Yeah, here is an example. So if you go to this website, you can play around with maps from all over North America, and it'll give you maps of the average wind speed depending on the altitude. So for example, this map we have 40 meters above the surface of sea level. So 40 meters above sea level, this is the average wind speed. And we can see on the east coast and around Newfoundland and the mouth of St. Lawrence, Nova Scotia, we have quite a bit of wind speed. So the dark blue is greater than 10 meters per second. And these are the average wind speeds from 2007 to 2013, 40 meters above the surface level, derived from modeled resource estimates at NREL via the wind toolkit. So what we would do is if we wanted to understand feasibility, we would first look at these wind charts and try to find where would be a good location to do our feasibility analysis on. After that, we would look at classifications of wind turbines. So aside from the classification of locations by their wind power density, wind turbines have their own classification system. And they're classified by the average wind speed at which they're capable of functioning efficiently. So these two tables here show table 4.1 from your textbook shows the classifications of locations by wind power density. So depending on the wind power density of somewhere we were to consider our analysis, if our wind power density, for example, was between 150 to 200 watts per meter squared, this would be a class 3 location. And typically, anything below a class 3 is not good enough. And then anything above a class 3 is okay. And then class 5, 6, 7, these are good. This is where we want to be. Anything, if we calculate the wind power density for some region and it's not high enough, then it's not feasible. It's not worth it to put wind energy there if we can find somewhere that has a higher wind power density. And then the next thing is to look at the classification of turbine that could be used in that area. So these are just some examples of the different classes of turbine, and it shows the average wind speed that they would be operating at and their turbulence ratio. So a class 1A wind turbine would operate well at an average wind speed of 10 meters per second, where if you had a lower average wind speed, maybe 7.5, you would choose a class 3 turbine. And then here's just a diagram to give you some perspective. Probably seen wind turbines when we're driving by a wind farm, or we can see them in the distance, but they are actually quite massive. And this is one of the really large offshore platform examples, but it's just shown to scale compared to an Airbus A380 aircraft. So each of those blades is quite long, or can be quite long. So they do get quite large. So how can we calculate wind power density? So we have Freud's theorem, which also includes the equation above. So I'll write that here. V is equal to V1 plus V2 over 2. And we have the power extracted by the turbine. The power would be the force times the velocity at the turbine, and we substitute in Freud's theorem. Then we get this equation here: 1/4 rho density of the fluid times the area swept by the blade times the product of V1 squared minus V2 squared times V1 plus V2. And then if we apply Bett's law, which tells us when we have a maximum efficiency, that maximum efficiency when the ratio of V2 over V1 is equal to 3. So we said Bett's law was our max efficiency was equal to 59.3% at 2 over V1 is equal to 3. Make sure that's correct. Yeah, so when V2 is over V1 is equal to 3. And so if we put this into our equation, then the maximum power that can be harnessed from a wind turbine, if we know the wind speed, would be equal to 8 divided by 27 times the density of air times the area swept by the wind turbine times the wind speed cubed. So the power available is highly sensitive to that wind speed. A small drop in wind speed is a significant drop in wind power. So let's look at an example where we are trying to do some wind farm feasibility study. So a wind turbine with a hub height of 40 meters and a rotor diameter of 60 meters is being proposed for a wind farm in Gaspésie, Quebec. The average annual wind speed at the proposed site is 7.0 to 7.3 meters per second. And the average annual air density, we'll say, is 1 kilogram per meter cubed. Let's estimate first the wind power density and assess the feasibility of using wind as a source of energy in this area. And then B, estimate the wind power that could be developed per unit area of land. So if we want to find wind power density is basically going to be the power available for some region based on the average wind speed divided by the area. So when we talk about density, in this case, we're not dividing by mass, we're dividing by unit of area. So we can write wind power density is equal to our max power available divided by the area. So if we do this, substitute in our equation, have our max power is 8 over 27 times rho times the area times V1 cubed. We end up with the areas canceling out, and all we have is 8 over 27 density of air times the velocity cubed, or the wind speed cubed. So for this site, it says that the average wind speed, and it shows there's a zoomed in map here. So where they're considering is probably this shade of blue here. So there might be one of these regions right up along the St. Lawrence. So this area here is Gaspé Peninsula. If we used average power, I suppose we would always try to select the correct wind turbine that would get us the closest as possible to that maximum power. And that's why we have our classification system. If we have it set up where we always calculate our wind power density this way, compare it to our tables, and if it's not class 3 or greater, then it's not really worth doing because achieving that kind of power is not overly reasonable. So this is convention. You could use average, but if we look for the max and we always follow the same rule and all of the tables are based on this type of analysis where we're looking for that max power, then it essentially would achieve the same thing. So the max power available would be, we have the density of air, we have to just choose now which velocity. So if this is our range that's given, then let's just choose the average. So let's say that V is equal to the average speed in that region. So 7.15 would be the average between 7.0 and 7.3. And that's what we'll use for our max wind power density or wind power density equation. So 8 divided by 27 times 1 kilogram per meter cubed times our velocity, so 7.15 meters per second cubed. So if we calculate this, we would be able to get 108 watts per meter squared. So calculating our wind power density by the convention, which is our max power divided by the area, and this is the area swept by a turbine blade, would be 108 watts per meter squared. So if we wanted to increase the power, we would have to choose a larger turbine blade. So let's compare this result now to our tables. So 108 would fall into class 2 system. So between 100 and 150 watts per meter squared. So if we're not above 150, this probably isn't a good site. So since 108 watts per meter squared is class 2, would say it's not feasible. And let's make a note here. The minimally accepted location would be a class 3. And that's greater than 150 watts per meter squared of area swept by the turbine. So this, make a note, is turbine area. So now let's find an estimate for the wind power that could be developed per unit area of land. So let's look at this. We want to find the power available per land area. So power per unit area of land. So this would be our max power divided by our land area. So how can we determine what our max power is here and what our land area is? So let's assume first that we have spacing between units of 10 rotor diameters. So that's enough to mitigate any interference from between these turbines. So they have to maintain 10 rotor diameters apart. So spacing between units of 10 rotor diameters, or 5 radii. So each turbine is in the center of a circle of radius of 5 rotor diameters. So if we have, let's draw our turbine here. The next one over the distance between these two would be 5 rotor diameters. So if this length of our rotor we call r, this distance here would be 5 times 2r, or 10r. So it says in the problem that our rotor diameter is 60 meters. So r is equal to 60 meters. So the distance between each one has to be 5 times 60 meters. So this would be 300 meters. So 5 times 60, 300 meters. So 300 meters is the distance between all of them. So the area covered by each unit, if we imagine that this is a perimeter, and we're making sure that no other unit comes within 5 times the radius of the blade, and the total area swept, land area, per turbine would be equal to pi times 300 squared. And this is 300 meters. And if we convert this to hectares, we would get 28.3 hectares. So 28.3 hectares of space per turbine. So now if we just take our maximum power based on the size of the turbine that we have and divide it by this land area per turbine, we can get the unit of power per unit area of land. So this would be equal to our power, which would be 305 kilowatts. So that's solving our P max equation for a rotor diameter of 60 meters. We get 305 kilowatts would be the power provided per rotor, per turbine, and divide that by 28.3 hectares, and we would get 10.8 kilowatts per hectare of land. So if we wanted a megawatt power supply, we would need about 100 hectares of land packed as densely as possible with turbines, and each turbine would have a blade length of 60 meters. We looked at a fixed control volume. We looked at a moving control volume at a constant velocity. Now let's look at some applications where we have an accelerating control volume. So for some problems, a few cases of problems, such as jet engines and rockets, our control volume is fixed to the shape and size of some accelerating body. So we can use Newton's second law, just like we did for a moving fluid. And in the Lagrangian description, as we know it, we have sum of the forces is equal to the time derivative of the momentum, which is mass times velocity. And our velocity is equal to the velocity of the control volume plus the velocity of the fluid with respect to the control volume. So if we substitute this in to our equation, we can write this in terms of the derivative of the mass times the time rate of change of the velocity of the control volume. And because of the continuity equation, the derivative of the mass with respect to time within the control volume is 0. So we only have this term, the derivative of the velocity of the control volume with respect to time. So the acceleration of the control volume, we can call it. I'll make a note here. Acceleration of CV plus the total derivative time rate of change of the mass times the velocity of the fluid with respect to the control volume divided by dt. So if we now input this into Reynolds transport theorem for linear momentum, we recognize that the last term is the equation for the time rate of change of our momentum of the system of fluid, and that's equal to our Reynolds equation for linear momentum. And substitute this back into our equation above. So this is Reynolds transport theorem. So if we substitute this back into this term right here, and then bring all of this back down, we get this last equation. So I'll erase those to remove some confusion. So what we were doing here is we have the sum of the forces is equal to the acceleration of the control volume plus the change in momentum of the system of fluid, which is through Reynolds transport theorem equal to the time derivative of the momentum of the control volume plus the time derivative or plus the momentum change across the control surfaces. So let's look at each of these terms. Sum of the forces is pretty familiar to us. Our mass times acceleration of the control volume center of mass would be this term that we talked about. The next term is the relative local change in momentum. And the last term is the relative convective change in momentum. So the convective change is always the change in something with respect to the change in position. So this result indicates that the sum of the external forces acting on an accelerating control volume is equal to the inertial effect of the entire mass contained within the control volume, plus the rate at which the momentum of the fluid system relative to the control volume's mass center is changing, plus the convective rate at which momentum relative to the control surface is leaving and entering. So let's take this big equation and apply it to some applications, turbojets and turbofans and rockets, and see how this can simplify for those applications. Let's look at turbojets first. So a turbojet operates by taking in air at its front, and then it increases its pressure as it passes through a series of fans, and that's called the compressor stage. So we have our gas entering the front, and it passes through a series of compressor fans. So as we're moving along this line here, we're increasing the pressure, we're compressing that gas, we're increasing its density. And then we have a highly compressed gas. It's now very hot because of the ideal gas law. We've increased pressure, then we've increased our temperature. And then we add some fuel to this mixture and we combust it in a combustion chamber, which causes rapid expansion of the gas. And then it moves through the exhaust. And as it's flowing out of the exhaust, we have some turbine blades down here to harness some of that energy. And we take that energy and we supply it back to the intake compression fan blades to run this machine. So like in a car, we have combustion that is driving a piston, and that is turning the motor. In a turbine fan or turbine engine, we have combustion of a gas that's running now a turbine blade, which is just rotational, and then that is connected rigidly or through a gear system, depending on the type of engine, to the intake compression fans, which help compress that gas, which is then used to combustion. So it's a complete cycle. In industry, you'll often hear of these kinds of engines. It's called suck, squeeze, bang, blow, which refers to each of those steps. So the suck phase, where air is sucked into the front, and then it squeezes the air in the compression phase. There's a big bang when you have combustion, and then the exhaust gases are blown at the end. So you ever want to remember the process of the steps for a turbojet or a turbofan, think suck, squeeze, bang, blow. So just like a propeller, the efficiency of a turbojet will increase at the speed the aircraft, as the speed of the aircraft increases, or as the speed that the engine is moving through air is increasing. So the speed of that air coming into the control volume, increasing that will increase our efficiency. Turbofans are a little bit different. They operate on the same principle, except there's this added component at the front. So the difference here now is we have a turbojet, so this region in the middle. So this is all the same, except now we have a big fan at the front, and we have this second pathway for air to flow. So this is just a two-dimensional cross section, but imagine this is a cylindrical cavity that's wrapped around our turbojet, and we connect rigidly this fan or through a gear system to control the speed of the fan, but the turbojet now is going to be driving this large fan, which is going to be blowing air through this secondary cavity, and that's going to generate more thrust. And typically we can get an increased amount of thrust with a turbofan versus a turbojet, but just because of the geometry, they tend to be quite large. But because of the increased thrust, this is the type of engine that you'll typically see on commercial aircraft. And then if you have a smaller aircraft, sometimes you'll have a turboprop system, which is essentially this, except now the fan blades are not blowing air into an enclosed cavity, it's an open cavity. So it's just blowing air past like an open propeller. So we can calculate the thrust for these both the same way. So to analyze the motion and the thrust of a turbojet or a turbofan, we'll consider a control volume that is encapsulating or surrounding the engine, and it contains all of the gas, air, and fuel within the engine. So if the engine is initially at rest, then the control volume will accelerate with the engine. If we draw our free body diagram and our kinetic diagrams, free body diagrams down here. The only forces externally acting on this, and we remember the forces of acting on the fluid. We have the weight of the fluid due to gravity acting downwards, and the force of the engine acting on the fluid would be in the negative x direction. And then in terms of the fluid motion around our engine, we have our mass flow rate in. So our mass flow rate of air. And then exiting, we have our mass flow rate of air plus fuel. We're burning fuel as we move along. And this will have some sort of exhaust velocity. And then the CV velocity would be the same thing as our aircraft velocity. So if it's initially at rest and we write our Reynolds transport theorem equation and we have our sum of our forces, this is the sum of our forces on this side. This is our Reynolds transport theorem equation. So all we have left, the only terms we have, is the mass times the acceleration of our control volume plus the mass flow rate of the air going in times the velocity of the control volume. That's the velocity of the air entering the front of our control volume, minus the mass flow rate of the air plus mass of the fuel, so that air-fuel mixture, times the velocity of our exhaust. So therefore, the thrust effect on the engine is caused by the mass flow rate. So we call this, these last terms here would be our fluid reaction. And the thrust is equal to the negative, or the opposite of our fluid reaction. So we see that we now have our terms just have the opposite sign. So our mass flow rate of our air-fuel mixture is now positive times VE, and minus the air-fuel, or the air mass flow rate, times the velocity of our control volume. So this is the equation for the thrust. So let's look at an example of a passenger jet. So we have a jet plane, it's in level flight, so it's horizontal with respect to the ground, and at a constant speed of 140 meters per second. Each of its two turbojet engines burns fuel at a rate of 3 kilograms per second. Air at the temperature of 15 degrees C enters the intake, which has a cross-sectional area of 15 meters squared. If the exhaust has a velocity of 700 meters per second, measured relative to the plane, determine the drag acting on the plane. So let's see, if we write down our equation from above, if it's horizontal, this term is going to go to 0, our cos theta, because we don't have any component of gravity acting against our direction of motion. So all we're left with is force of drag is equal to the acceleration of our control volume times the negative thrust. So we have, let's see, negative Fd is equal to mass times the time derivative of our control volume. Since they're all in the same direction, we can just resolve this in the horizontal direction. So we'll write this in component form. Plus the mass flow rate of the air times the velocity of our control volume minus the mass flow rate of the air-fuel mixture times our exit velocity. So this is the equation we're trying to use. This is what we have available to us. And the question asks, determine the drag force acting on the plane. So find Fd. So let's figure out what each of these terms are. So it's traveling at a constant speed of 40 meters per second. So that's the velocity of our control volume. So the velocity of our control volume is equal to 140 meters per second. Each of his two turbojet engines burns fuel at a rate of 3 kilograms per second. So our mass fuel rate consumption is 3 kilograms per second. That's a mass flow rate of our fuel. The air has a temperature of 15 degrees C. And if we were to look up our density, this would be a density of 1.23 kilograms per meter cubed. And this would be at the inlet. And it enters the intake at a cross-sectional area of 15 meters, or 0.15 meters squared. So the area in we'll call area A, I'll leave it an area in, is equal to 0.15 meters squared. So we can calculate the mass flow rate of air in from this. Mass flow rate of the air now is just equal to the density of the air times the velocity of the control volume, which is the relative velocity of the air entering the control volume, and times the area. We have the area is 0.15, so this is 1.23 kilograms per meters cubed, times the velocity, which is 140 meters per second, times the area, 0.15 meters squared. So our mass flow rate of air is 25.83 kilograms per second. We'll go through this question, then I'll answer some questions in the chat. So we have the mass flow rate of the fuel, we have the mass flow rate of the air, we have the velocity of the control volume, we have the velocity of our exhaust gas, 700 meters per second. Measured relative to the plane. So do we have enough now to solve our equation? We have this, we have this, we have these two, we have the exhaust. What about this term? Right, so right in the question it says our aircraft is traveling at a constant speed, so it's not accelerating. So this term just becomes zero because we have a constant speed. So let's rewrite our equation now. We have the drag force is equal to 0 plus mass flow rate of A, so velocity of the control volume, minus mass flow of the air plus fuel, times the velocity of the exhaust gas. So this is equal to mass flow rate of air, 25.83, times the velocity of the CV is 140 meters per second, minus 25.83, plus the burn rate of fuel, so 3 kilograms per second, times the exhaust, 700 meters per second. Calculate this, the drag force would be 33.13 kilonewtons. So at this point, when we have zero velocity, the thrust is equal to the drag. So we notice that this is our minus thrust. Our minus thrust is equal to our negative drag, so it's our thrust is equal to our drag. Yeah, so in the chat, there's a question. This should be all multiplied by 2. Thanks for catching that. It says in the question that there are, where does it say this? There are 2. If each of it's 2 turbojet engines. So the total drag would be the thrust of each of those engines added together. So 2 times this quantity. Maybe I'll make the brackets a little more clear. So this equation here would be for each engine. So just to go over again why the drag force is equal to the thrust. When we're traveling at a constant velocity, we just write our sum of the forces. Sum of the forces on the system, we could say, is equal to drag force, let's say our aircraft, so we're just looking at the forces acting on the aircraft now. We have our drag force, and we have our thrust, we have our acceleration. So the total forces acting on the aircraft, where the thrust we can calculate from that fluid flow. The drag force is in the negative direction, so minus drag, let's say this is positive, plus thrust is equal to acceleration. Sorry, mass times acceleration. Which we said up above was our mass times the acceleration of our control volume. So that's the same thing as our acceleration. So if our control volume is moving at a constant velocity, then if A is equal to 0, then all of the force of our thrust is just to overcome that drag. So just by equating our equation of motion, solving our equation of motion with acceleration to 0, the forces must balance. So thrust force is equal to that drag force, which is exactly what the result of our Reynolds transport theorem equation gave us. If the acceleration of our aircraft is not 0, so we're taking off or we're landing, these forces are not in balance anymore. And the difference is the mass times the acceleration of the control volume. So that's turbojets and turbofans or turbomachinery relative to aircraft. Let's quickly look at rockets and see how we can apply Reynolds transport theorem to the accelerating control volume around a rocket. So first, I think rockets are fascinating, but a rocket engine, we just do a crash course quickly on the types of rocket engines. They can either burn solid or liquid fuel that's carried within the rocket. So a solid fueled engine is designed to produce a constant thrust. And it can produce this constant thrust by forming the propellant into a shape that provides a uniform burning. So more or less the area that's exposed or is burning in this fuel inside the rocket is burning at a constant rate, which is generating a constant rate of thrust. Very important with solid rockets, once you ignite it, it cannot be controlled. Because it is solid, it cannot mix with air or mix with a fuel propellant to ignite. You have the mixture of the fuel and air in the solid itself. So everything it needs to combust is right there. So once it's lit, there's no stopping it. Think of it kind of like a firework. So this is kind of a simplified version of the geometry where you would have your fuel and an igniter. So this is your fuel here. You'd have an igniter in the middle, and then the fuel is burning from the inside out. And as it burns, it only has one way to go. and it ejects out this nozzle, and then the design of the nozzle can actually direct that expanding gas flow, and that's what generates the thrust in the rocket. So the other kind is a liquid-fueled rocket, and this is the kind of rocket that was used in the Saturn V Apollo missions. So this requires a more complex design, but you can control the rockets, and you can turn them off because they require fuel to be added. So it involves a system of piping, pumps, pressurized tanks, and it operates by combining the liquid fuel with an oxidizer as the fuel enters a combustion chamber. So you can control the thrust by adjusting the flow of the actual fuel. And oftentimes you can tell that a rocket might be liquid because it is usually using liquid nitrogen to keep the fuel cold enough to be in a liquid state, and it's under a lot of pressure. And so you can just see on the Apollo rocket here that this is just liquid nitrogen leaving the rocket. And that's just used to cool down that fuel. So how do we calculate thrust on a rocket? The performance of these types of rockets can be studied by the same process as we did for our turbo machinery. So we can apply the same equations, the Reynolds transport theory equation and the conservation of mass, or continuity equation, and we would put our control volume around the entire rocket. So if we did all the same things as before, the only difference we would have is a turbojet or a turbofan has a mass of air entering the engine and exiting, whereas with a rocket, we don't actually have any fuel or air entering because it's already on the rocket. And so our MA value, the mass of the air entering, is equal to 0. So it's only the fuel that's used. So we just have the fuel burn. So we can simplify our equation quite a bit, and we only have, if we assume the rockets are traveling vertically, then we have negative force of gravity, the weight due to gravity. We can say this is equal to mg. Our drag force, which is equal to mass times acceleration of the rocket, minus the mass flow rate times the exhaust velocity. And just like with thrust, this is relative to rocket. That's relative to the velocity of the rocket. All right. So we have our equation. That was a very, very quick breakdown of rockets. But if we just look at the Reynolds transport theorem, and we already did all the work with our deriving our equations for thrust of turbofans and turbojets, we applied the same principles and just notice that some of those terms go to 0 because there's no air mass flow rate entering our control volume anymore. So we took a quite complicated looking problem and we simplified it in this nice convenient equation. So let's look at this example. We have a rocket and its fuel. They have initial mass of 5 megagrams. When the rocket takes off from rest, the 3 megagrams of fuel is consumed at a rate of 80 kilograms per second. And it is expelled at a constant speed of 1,200 meters per second relative to the rocket. Determine the maximum velocity of the rocket. Neglect the change in gravity due to altitude and the drag resistance of the air. So if we were to solve this problem realistically, these rockets are traveling so far that the effects of gravity on our weight term here changes with altitude. So this term here would change with our altitude. And then our drag force would change with velocity. And typically it's proportional to the velocity squared. And it would also change with the density of the air, which changes with altitude. So these are where the problems become quite complicated, is understanding the forces acting on a control volume. The acceleration of the rocket, that's exactly what it's going to be. And then the mass, fuel rate, and the velocity of ejection, that's the momentum of the fuel leaving the rocket. Those are pretty much constant. Those aren't going to change too much in real numbers than what we calculate here. What adds a lot of complexity is this, the forces, external forces acting on the control volume. So if it says we can ignore the drag force, so we're assuming that there's no friction, maybe this is in a vacuum, then our equation becomes, we have negative W is equal to mass times the acceleration of the control volume minus the burn rate of our fuel times the velocity of our exhaust, the exhaust velocity. So the question says, determine the maximum velocity of the rocket, neglect the change in gravity due to the altitude and drag resistance of the air. So we've already neglected the drag resistance, that's that FD term, so that equal to 0. So how can we solve this? First, let's recognize that the velocity of the control volume is the same as the velocity of the rocket. So we're asked to find the maximum velocity. So we know how much fuel is on the rocket, and we know the burn rate of the fuel. So we can figure out how much time it's going to take for that fuel to burn up. And at that point, the rocket no longer has anything to accelerate it any further. So the acceleration is going to stop, and the only thing acting on it then would be the force of gravity. So we'd reach a maximum velocity at that point. So what we got to do is we got to figure out how long it's going to take for that mass or the fuel to burn up. And then we can rearrange this equation and we can integrate the velocity with respect to time. If we know that final time, we can find the velocity after that amount of time has passed. So if we know the mass fuel rate is 80 kilograms per second, and the mass of fuel is equal to 3,000 kilograms, or 3 megagrams, then we can write the total mass of the aircraft is equal to the initial mass of the aircraft, 5,000 kilograms minus 80 times t seconds, because it burns it at a constant rate. Let's just write the units of kilograms outside here. So this is the mass of our rocket. So if we look at this, it should be 80t, not 8t. So when time is equal to 0, before any fuel is gone, our total mass of the rocket is 5 megagrams, 5,000 kilograms, which matches the question. And so how long is it going to take? What is time when 3 megagrams of fuel has burned? So basically, T flight is going to be equal to the mass of fuel, or sorry, the mass of the fuel divided by the mass burn rate of fuel. So it's going to be equal to 3,000 divided by 80. That's kilograms divided by 80 kilograms per second. We should get a time of 37.5 seconds. So that's how long our fuel is going to burn for. So we essentially now need to find the velocity at that amount of time. So this is equation 1. Let's go back to equation 1 again. So we can rearrange this. Let's write our derivative velocity over control volume is equal to our weight due to gravity, which is m times g, plus our mass burn rate of fuel times the exhaust velocity. And let's move our mass, our m, over to this side. This is all times dt. So all I've done is rearrange that first equation above, right here. So I moved all of our non-accelerating terms, w, mf, and ve, to one side, divided by mass, and multiplied by dt. So we can integrate both sides of this equation now. And on the left, we're going to be going from 0 to our velocity when we run out of time. And on the right, we're going to be going from time 0 to time t flight. So that total length of our flight. So the left-hand side just becomes our velocity. Let's call this V max. And if we integrate, this is from 0 to 37.5 of our mass times our gravity. So if I take the first term, this is just equal to g and the second term becomes our mass flow rate. So that's 80 times our exhaust is 1200 meters per second. Yeah. And our mass is a function of time. So we have to include this, and it's 5,000 minus 80 times t. Let me just write in this gravity constant. All multiplied by dt. So I want to make sure I have this correct. I feel like I'm missing a negative sign somewhere. Yeah, I think mg should be negative, because we're assuming upward is positive, so mg is in the negative direction. So this ends up being negative 9.8. There. So if we integrate this, we're left with negative 9.81 t minus 1200 times ln of 5,000 minus 80 times t. So we finally get our velocity, 1200 ln of 5,000 divided by 5,000 minus 80 t minus 9.81 t. So if t is equal to 37.5 max velocity, we solve this would be equal to 732 meters per second. So that's rockets. We saw this quote last time, so I'll leave you here again, and we'll come back and we'll introduce conservation of energy.